Okay, now let's continue. When we have a circle, gamma is a circle in C infinity. So gamma could be a circle in complex plane or straight line. And we define orientation to be a ordered triple. Z1, Z2, Z3 is an ordered triple. On this gamma, which defines an orientation. Right? This is what we learned last time. It's like this. Have here, this is Z1, Z2, Z3. Follow the order, you will get a direction. You will get direction. Okay, if you have just a straight line, then you have to be careful. Okay, if you have just a straight line. For example, let gamma be R straight line, but it's still a circle in C infinity. We choose 3 points to define an orientation. Let Z2, Z3, Z4 be on gamma. Of course, you must have the orientation. If you, for example, if you have this way, this is Z1, Z2, and Z3. Well, you will imagine that you go from Z1 to Z2 and go to infinity and pass infinity back to Z3. This is the orientation. That's strange, but it's orientation in C infinity. Okay? This is an orientation in C infinity. If you have an orientation in C infinity, if you have Z1, Z2, Z3, this is just a regular direction in C. An orientation in C. It's also an orientation in C infinity and the C infinity. Okay, so there's small difference. Okay, now we know that if we have the cross ratio, define T of Z to be Z, Z1, Z2, and Z3. And Z1, Z2, Z3, they are all real numbers. So it is AZ plus B over CZ plus D with A, B, C, D all real. Right? With A, B, C, D all real. Because by the definition of a cross ratio, you can imagine that you can really do that computation. It has to be the real one. Another thing, if a Mobius transformation T, not necessarily this T, arbitrary Mobius transformation T maps real line to real line, then TZ equal to ABCD. And ABCD can be chosen as all real numbers. All real numbers. Right? We did the proof about this. Okay, so either way, when we have such stuff, by this cross ratio, we just get ABCD are all real numbers. Remember that they are all real numbers. Now let's do a little bit discussion. So this cross ratio, it is AZ plus B, CZ plus D. Remember that we don't want the division by a complex number, so we multiply top and bottom by the complex conjugate. Okay, because C and D are both real, so you don't have to put a complex conjugation. And this is AZ plus B times CZ bar plus D over magnitude CZ plus D squared. And then you multiply the numerator. You will get what? You will get AC Z modulus squared plus BD and plus BCZ bar and plus ADZ over this number. This number is a real number, so division is clear. Okay, just plain multiplication. Okay, and then let's check. This is real. This is real. This is real. Only this part will provide the imaginary part, right? Only here. And you have Z bar. You have Z bar, you get a negative sign. So we get the imaginary part of Z, Z1, Z2, Z3, the imaginary part of a TZ is equal to, you see here, this is the real part of Z minus imaginary part of Z times I. And then times BC, right? Times BC. So you will get BC negative BC imaginary part of a Z. Here is a real part of Z plus imaginary part of a Z times I. So it's a plus AD imaginary part of a Z. And then over this denominator, real denominator. Correct? So if we factor out the imaginary part of Z, we will get AD minus BC over CZ plus D modulus squared times imaginary part of Z. And remember that we assume AD minus BC is not 0 for the in the definition of Mobius transformation. So this is a non-zero number. It could be positive, it could be negative. Denominator is always positive. All right, so what we get? We get the imaginary part of the image of Z under this cross ratio. Imagine part. Remember that imagine part. If you have a Z, I am Z positive means it's upper half space. I am Z negative, it's a lower half space, right? So here is you will get a positive and negative, but this is positive. It does not change the sign. AD minus BC could be positive or negative, so you may have different sign compared with related to the imagined part of Z. So you can put here imaginary part of this cross ratio is greater than 0. This is determined by this AD minus BC, also determined by the imaginary part of Z. Right? So this is either upper half space, plane, or lower half plane, complex plane, right? It will represent either upper half plane or lower half plane. And this upper or lower will be dominated by the AD minus BC. If AD minus BC positive, then this is the upper half plane. If AD minus BC is negative, this will be lower half plane. All right? So in other way, in this sense, this AD minus BC, they also call it the determinant of D is also called the determinant of T, of the Mobius transformation. Okay, it may change the upper or lower half space, half plane. All right. Okay, so this is a case when we have the straight line, even not all straight line, just this real line. And if we have an arbitrary circle, so now assume that gamma is an arbitrary circle, and Z1, Z2, Z3 are on gamma. Okay, then let's see for any Mobius transformation, for any Mobius transformation, S is arbitrary Mobius transformation. The imaginary part of Z1, Z2, Z3 greater than 0. Well, the cross ratio is compatible with the Mobius transformation. So even before the imaginary part, you apply the cross ratio, they're equal. So you put S of Z, S of Z1, S of Z2, S of Z3 greater than 0. Okay, so this is exactly the same thing. You can compute S of Z and the cross ratio, or you can directly compute the original one. They have the same value. Same value, of course, have the same imaginary part. All right, and then we let W be S of Z. Let W be S of Z. Okay. So let's check then. Imaginary part of W, and it becomes W, S of Z1, S of Z2, S of Z3 greater than 0. I just use substitution, and Z becomes S inverse of W, S inverse of W, right? Whenever you have a complex number such that this cross ratio has a positive imaginary part, you apply S inverse. So you can move this S inverse outside of it. And then you replace this W by Z. You can use whatever letter, right? You replace this W by Z. So that's why in the textbook they skip several steps, directly give you S inverse of Z, imaginary part of Z, SZ1, SZ2, SZ3. All right. So in the textbook, these two steps are skipped. So you directly get the first line, second line, and third line. But that's exactly the substitution, just substitution. All right. So that's the computation. From the computation, let's check. This is for arbitrary S, Mobius transformation. You always have such a thing. If this S is chosen, remember we can choose S to fit some pairs of circles. If S is chosen to map gamma onto R infinity, so we're trying to map gamma to R infinity. Okay, then what? Then this is a real number. This is a real number. This is a real number. right? Then this and this imaginary part of z as z1 as z2 as z3 greater than 0 will represent represents either, we don't know, either the upper half plane or the lower half plane. Right? So this is either upper half plane or lower half plane based on the previous argument, because you have numbers, real numbers. And this is a upper or lower half plane. You apply the S inverse, you map it to the new region. The new region is the region of Z such that the imaginary part of this cross ratio is positive. Okay, so the set Z imaginary part of Z1, Z2, Z3. So this cross ratio is the image of either upper half plane or lower half plane under S inverse. You use S inverse to map either upper half plane or lower half plane to a new region. That region is this part, is this set. Okay, and this S is specially chosen. S will map gamma onto R infinity. S will map gamma onto R infinity. For example, S could be the cross ratio. The cross ratio map Z1 to 1, Z2 to 0, and Z3 to infinity. Right? For example, S of Z is equal to Z1, Z2, and Z3. Then it will map gamma to R infinity. Okay? And then you apply this S to Z1, Z2, Z3. Correct? It's well, this is just one of a choice. It's not unique at all. Now, because it is an image of either upper half plane or the lower half plane, let's define the sides of gamma. So, if Z1, Z2, and Z3 is an orientation of gamma, then we define the right side of gamma, of course, with respect to Z1, Z2, Z3, with respect to this orientation, to be right side is a region, to be the set Z such that the imaginary part of the cross ratio is greater than 0. This is the right side. Why do we define this as a right side? It's because of the following example. For example, if you have complex plane, and this is a real line, and you have number 1, 0, and infinity. Then the cross ratio z 1 0 infinity is z, and its imaginary part of this cross ratio positive means when you move from 1 to 0 and to infinity, this way, this is the upper half plane. Upper half plane is here, right? It's on the right side when you're heading from right to left. When you're heading this way, this upper space is the right side. That's a reason to give such name. Okay? Oh, sorry. So, when you have such thing, you move from 1 to 0 and to infinity. You go from right to left. You go this way, and this is right side. Parallelly, we define the left side of gamma, of course, with respect to the orientation, because you're already heading to the left, heading to the west. So this is the right side. The north part is the right side. If you change your direction, of course, you're going to change your side, right? So we define the left side of gamma. You should also emphasize with respect to Z1, Z2, and Z3 to be the region Z, imaginary part of a Z, Z1, Z2, Z3 become negative, right? So positive right side, negative left side. If it is equal to 0, that's a line. Because when imaginary part is equal to 0, it's a real number. This cross ratio becomes a real number. When cross ratio becomes a real number, it means you are on the circle. But this circle is represented. Yes, it is on the circle of gamma. There's no side. When this imaginary part is 0, it becomes a real number. Real number means gamma is z is on the gamma, not on the sides of gamma. Right? Okay, so now we do have line like the cutting part, and we have orientation. With orientation, we have left or right. And what is next property? The next almost obvious property is called the orientation principle. Orientation principle. Orientation principle says let gamma 1 and gamma 2 be two circles in C infinity. We're talking about C infinity. We try to unify the circles with the straight lines in C. And let T be a Mobius transformation such that T of gamma 1 is equal to gamma 2. So T is a Mobius transformation between gamma 1 and gamma 2. And let Z1, Z2, Z3 be an orientation for gamma 1. You have orientation for gamma 1. Then T, the Mobius transformation, will take the right side under the left side of gamma 1 onto the right side under the left side. Of gamma 2. Okay, so here gamma 1 has orientation. What is the orientation of gamma 2? It is with respect to the orientation, of course, determined by the orientation of gamma 1 and t. T of z1, T of z2, and T of z3. T of z1, z2, and z3. Okay, so this is the orientation principle. Actually, it's natural because the orientation is determined by the cross ratio. But the cross ratio is compatible with whatever Mobius transformation. Right? So if this is a positive, well, actually this one is equal to this one. This one is positive, here is positive, so you just collect the corresponding image and that's it. That's it. Right? So it's actually like this. You map T. You use T to map this part to this. This is exactly the right side. Okay, you try to make this writing clearly. Like the pre-image is mapped to the image. What is a set of image and what is a set of a pre-image? Okay, but the idea is just the cross ratio is compatible with a Mobius transformation. Okay, so that's a orientation principle. That's a orientation principle. And now let's study some construction problem. We have the following problem. The previous part, we always discuss curves, circles, straight lines. We get the map. Now we have regions, left side and right side. We want to construct the analytic functions between regions. So the problem is the following. Find an analytic function f from G to C, where G is the upper half plane. G is the upper half plane, such that f of G is equal to the unit open disk. Unit open disk. Upper half plane does not include the real line. Okay? We're trying to do such problem. So upper half plane. And unit circle, unit disk. Right? Unit disk, we want to do that. Well, in this process, we do not directly construct this. We do not directly construct this. No, not upper, real part, my bad. This is imagined part. The right half plane, not upper half plane, right half, right, sorry. the right half plane. I think the other stuff, yeah. My bad. The right half plane, this is right. Right half plane. Okay, so we want to construct some analytic function like this. Instead of do such construction, we are going to do the following one. We're going to construct an analytic function, a Mobius transformation from right half plane to the upper half plane. We also want to construct the unit disk to the upper half plane. Now this is upper half plane. The reason we are interested in the upper half plane is that its boundary, like the cutting line, is R. That's advantage of upper half plane than the right half plane. Why we are interested in this? Because cross ratio will easily map whatever circle to the straight line, real line, to the real line, right? Okay, now let's see. This is right, my bad. Now let's see. We define what? We define this S of Z to be the cross ratio Z, negative I, 0, and I. How do I get this cross ratio? This is a right. How do I get a right? I get a negative I and 0 and I. So by this order, this is the right side. And this cross ratio will map this imaginary axis to 1, 0, infinity. For 1, 0, infinity, upper half plane is also the right side. Okay, so by this, we can have, by the orientation principle, we will map the right half plane to the upper half plane. Okay, right half plane to the upper half plane. And this one, let's check. It's a Z minus Z3, Z minus Z4 over Z2 minus Z3, Z2 minus Z4. Okay, so this is negative I over negative 2I is 1/2. You flip 1/2 upward, it's a 2Z over Z minus I. 2Z over Z minus I. That's a cross ratio of it. And this cross ratio will do this job. And we can also verify that it really mapped the right half plane to the upper half plane. How do we verify it? We just multiply top and bottom by the complex conjugate. Right? You get conjugate of Z and the conjugate of I's. And this is, the denominator becomes, okay, numerator is 2. Denominator becomes Z minus I modulus squared, whatever is a real positive real number. And then you have Z times Z bar modulus of Z squared plus IZ. Okay, and this Z comes from G. This is set G. This is set D. Z is inside the G. It means the real part of Z is positive. Real part of Z is positive. Then this is real. The IZ, the imaginary part of IZ, is the real part of Z because you multiply by I. So it's also positive, right? Imaginary part of IZ is real part of Z is positive, so it's upper half plane. upper half plane. Okay, so this is only verification, which tells us we do map the right half plane to the upper half plane. But by the orientation principle, it's guaranteed already. Okay, so that's a one Mobius transformation analytic function. Let's consider the other one. For the other one, I want the right side to the right side. How do I get the right side? You just go clockwise. The interior part is the right side. Go clockwise, there are several, infinitely many choices. So we can choose, for the computation purpose, we choose this triple. Of course, you can choose whatever other triple, but the solution will be slightly different. We choose this because the mathematicians already did a lot of computation. This selection will give us the most simple formula. All right, so we will choose a cross ratio R over Z as a Z, negative I, negative 1, and I. Z negative I, negative 1, and I. So it's a Z minus Z3 over Z minus Z4, Z2 minus Z3 over Z2 minus Z4. Okay? So what this is, it's a 1 minus I, it's a negative 2I. So you have negative sign, you got 2I, I minus 1. I don't want a negative sign. And then you have a Z plus 1 over Z minus 2. Z minus I, my bad. Z minus I. Z plus 1 over Z minus I. Okay, so this is R. S and R are both cross ratio. They have inverses. So what is F? F is F or T. T is R inverse of S composition. R inverse of S will map G onto D. Will map G onto D. Well, it really takes time to compute it. You can check that if you have R of a Z as a AZ plus BCZ plus D, then R inverse of Z will be DZ minus B negative CZ plus A, right? You change the sign of a B and a C, exchange A and D, and then you compose with S. I'm not going to do that, but after the composition, you will get T of Z is equal to Z minus 1 over Z plus 1. All right, so this is the simple formula. It depends on your selection, negative I, negative 1, and I. Okay, otherwise you would not get a better one. Okay, so this is a Mobius transformation. It is also Mobius. This is a Mobius transformation from the right half plane to the unit circle. It's better for you to keep in mind. It maps negative I, 0, and I to negative I, negative 1, and I. There's a one-to-one correspondence. How do I know it? This one is mapped to 1, 0, infinity. This one is mapped to 1, 0, infinity. So see here. So that's why it's negative I to negative I, 0 to negative 1, I to I. All right. And keep this in mind. And let's check the other one, the other function. Exponential function. Exponential function, e to z. E to z is e to r I r z is r e I c, no, or what is this? R not r, it's x plus I y. X plus I y, it's e to x and cosine y plus I sine y, right? Okay, so how do I get right half plane? Right half plane means the imaginary part should be positive, so we choose y belong to what? Belong to negative pi over imaginary part. Okay, yeah, this is what imagine real part. This is a right half plane. I keep thinking about the upper half plane. This is a right half plane. Right half plane. Right half plane, the real part is positive, so cosine y should be positive. Cosine y positive, then y is between negative half 2 and positive half 2. Well, we just choose this band. We choose this band. So y is between negative half 2 to positive half 2. This is a region. Horizontal strip. And exponential function e to z will map it to the right half plane. Right half plane, because the real part is positive. R of ez is greater than 0, because cosine y is greater than 0 over this direction. And the real part is mapped to the unit disk by the z minus 1 over z plus 1. Z minus 1 over z plus 1. So after you compose it, we get another one. We get the f of z, which is e to z minus 1 over e to z plus 1, maps the horizontal strip, the z part, imaginary part of a z, y, right? It's between negative half 2 and positive half 2. Up's value is less than pi over 2. This horizontal strip, map this onto the unit circle, a unit disk, d, which is z, the modulus of z less than 1. That's the composite function of exponential function with this function we just discovered, z minus 1 over z plus 1. All right, so that's a very nice function. So later, after this study, if you see other similar argument with different region, it's better for you to collect them and the argument with as a dictionary, so that every time you have a problem, you can either recall them or search for them. All right? Okay, so let's see the other one. For example, if we have the region, what is the region? The argument of z, the argument of z is bounded by pi over 2. Pi over 4, my bad, pi over 4. If this is argument, this is a pi over 4, this is pi over, the other part is another pi over 4. If this is the region, It's a sector, infinite sector. How do we map it to the unit circle? We first square it. We apply z squared. Z squared will amplify the argument. You see, z squared REI theta squared is r squared EI 2 theta. So theta is between negative power 4 and power 4. 2 theta will be between negative power 2 and power 2. So this is the real part, positive. So this is a right half plane, and then you apply z minus 1 over z plus 1. You will map it to the unit disk. So the composite function will be z squared minus 1 over z squared plus 1. Right? So if you have the region, if you have this sector not exactly power 4, for example, it's just alpha, alpha, you are going to do what? You are going to apply the function alpha over 2. You are going to apply the function z to the power alpha over 2, right? Z to the power alpha over 2, and then this power will help you to expand this sector to the right half plane, and then you apply this this important Mobius transformation z minus 1 over z plus 1. You will get z to the power alpha over 2 minus 1, z to the power alpha over 2 plus 1. This is the transformation analytic map. Of course, here you are going to just choose the branches. Okay, so also if your sector, for example, your sector is this, it's not purely symmetric with respect to the positive real axis. If you just get the first quadrant, if you get the first quadrant, this is an argument of z is between 0 and pi over 2. So how do you do that? You rotate it How do we rotate it? Z e to negative I pi over 4. We choose half and multiply by the negative. E to the negative I pi over 4 will rotate it clockwise. Subtract argument. So you rotate clockwise. Then this one will turn to here. Turn to the first case, and then you apply the whole stuff. Okay? If you get the quadrant 4, you have quadrant 4, you are going to rotate counterclockwise, right? You get counterclockwise. If you have quadrant here, then you're going to apply z times e to I pi over 4. Add pi over 4, you will change it to this part. So anyway, we try to rotate it so that the sector is symmetric with respect to the positive real axis, and then we choose a proper power function to make it exactly the right half plane and apply z minus 1 over z plus 1 to map it to the unit disk. So that's the general strategy for such problem. Okay, so let's finish this video at this moment. We will continue the lecture in the next video. Okay, the lecture is not done. Thank you.